Comparative analysis of truss bridges. Abstract: a bridge must be designed to safely resist all loads and forces that may reasonably occur during its life. These loads include not only the weight of the structure and passing vehicles, but also load from natural causes, such as wind and snow. The loads may act individually but more commonly occur as a combination of two or more loads applied simultaneously. The project discussed analysis and design of steel truss bridge. The bridge is 70 m long and 7.5 m width and 6 m high. The spaces between the trusses in the roof are various. From the beginning we leave space that equals 0.5 m. The analysis was done by staad program. The project studied maximum axial forces, shear forces, torsional values, and moment. Keywords: Pratt truss bridge, how, Warren, staad Pro V8I. Introduction. A bridge is a means by which a road, railway, or other service is carried over an obstacle such as a river, valley, and other road or railway line, either with no intermediate support or with only a limited number of supports at convenient locations. Bridges range in size from very modest short spans over, say, a small river to the extreme examples of suspension bridges. The main advantages of structural steel over other construction materials are its strength and ductility. It has a higher strength-to-cost ratio in tension and a slightly lower strength-to-cost ratio in compression when compared with concrete. The stiffness-to-weight ratio of steel is much higher than that of concrete. Thus, structural steel is an efficient and economic material in bridges. Objectives of the present study. 1. To determine the reactions and member forces. The methods used for carrying out the analysis with the equations of equilibrium and by considering only parts of the structure through analyzing its free body diagram to solve the unknowns. 2. Create a structural optimization algorithm capable of finding the various reactions, when subjected to various load combinations and design constraints. 3. Comparing and analyzing the various constraints of different truss bridges models. Various truss bridges. Pratt truss bridge. This type of truss has diagonal members that slope down towards the center. This type is completely differing of the Howe truss. The inner diagonals of the truss are having tension, whereas compressive force acts upon vertical members. This truss was invented by Caleb Pratt and Thomas Pratt in 1844. This type is practical for spans up to 75 meters. Warren truss bridge. It was patented by James Warren in 1848. It consists of longitudinal members joined by cross members that are angled. Its forms, alternatively inverted equilateral triangles, ensure that no strut, tie or beam is subjected to bending or torsion strain nature forces. See loads on truss bridges. Dead load. The mass of the equipment load that has constant magnitude and attached to the structure permanently represents the dead load. It consists of the main truss weight, the floor beams or girder weight, and stringer of the floor system. The dead load that acts on the member should be assumed before the design of the member. A member of structure should be designed in such a sequence that to as great an extent as practicable the weight of each member designed is a portion of the dead load carried by the next member to be designed. Live load. There are mainly 4 types of loadings whose usage depends on the purpose, location, and properties of the bridge. There are following type of loadings as listed. IRC Class 70R loading. IRC Class A loading. IRC Class A loading. IRC Class B loading. 2. Problem statement. Analysis of steel truss bridge. The bridge is 70 m long and 7.5 m width and 6 m high. The spaces between the trusses in the roof are various. From the beginning leave space that equal 0.5 m, after that divided all spaces in 10 segment the length of each one equals 7 m in the floor. Project used the straight member and, in the beginning, and the end connected by welding point formed triangles, and this member affected by compression or tensile force. About the moment the same mean of torque is excluded in the trusses. Moreover, assume all the joint in the trusses is pin. 3. Result and discussion. Comparative results of shear force, in Kn. 4. Conclusion. This project discussed the analysis and design of steel truss bridge. the bridge is 70 m long and 7.5 m width and 6 m high. The spaces between the trusses in the roof are various, from the beginning by leaving space that equals 0.5 m, divided all spaces in 10 segment the length of each one equals 7 m. 1. Maximum shear force value is for how truss bridge which is 485.763 knots. 2. Maximum displacement is 690.141 mm for Warren truss bridge. This is 15% more than Pratt truss bridge and 5% more than Howe truss bridge. 3. Torsional value for Pratt truss bridge is 30% more than Howe truss and 22% more than Warren truss bridge. 4. Maximum support reaction is 4,946.319 knots for Howe truss bridge. 5. Maximum moment occurred for Warren truss bridge which is 1029.88 kNm. This value is 25% more than Pratt truss bridge.